In the previous video I showed a brief demonstration of some firmware test routines that I'm writing, and I thought in this video it might be interesting to expand a little bit on those test routines and show you through the first batch that I've created and what they're used for. The machine itself is quite complex, and because of the nature of the firmware that it runs, it's very difficult to fault find on. It's kind of an all or nothing, where it either works or it tends to show nothing at all, and then you're left going through all the hardware trying to find exactly where the problem is on a hardware level. But what I wanted to do, bearing in mind how many faults I found on this machine already, is to have the machine itself help me in the fault finding process. So to that end I've written a series of test routines, and the test routines are programmed into the ROM that I've got fitted into this new ROM card that I've made. Now, one thing to bear in mind when testing this machine is that for anything to work at all, including any firmware on the ROM card, then quite a lot of the machine has to work to start with. So for example, the CPU that resides in the 4 cards down here has to be working to a fairly large degree, and that can be quite difficult to fault find on. But again, if you have a consistent program that you're trying to run, such as a very simple test program on the ROM, then it's much easier to fault find, because you can trace through a single path on the microcode generator card to see exactly what the machine is doing. And that's what we're doing here. So I'll demonstrate a few of the tests and explain very briefly how they work. So the first one is a sounder test. It might seem like just beeping something is not very useful, but bear in mind, for this to work, then a lot of the CPU has to work. So all 4 CPU cards have to be working to a good degree. The M register card needs to be working to a good degree, so does the T register, and of course the ROM card needs to work. But because this is a replacement ROM card that we've made, then we can be fairly certain that once it's been tested, which it has, then it will work. And of course the board that houses the sounder itself has to work. It's not just as simple as setting a single line. It is firmware that you have to run to make the sounder operate. So if I power up the HP, you can hear the sounder beeping, and that's what the firmware is set to do. It just beeps the sounder periodically. Quite a lot is going on to make that happen, so it really assists in the fault finding. You can trace through exactly what the machine is trying to do. Turn it off. I've mentioned previously these switches on the ROM card, and they allow me to select between different banks within the ROM itself. So we've gone through the sounder test routine, so the next switch position will take us on to testing the RAM board. To do this I need the analyzer on, so I'll power up the analyzer, point the camera at the screen, and then we can see exactly what's going on. Before I do that, I need to select that particular test, and it's just as simple as setting the correct switch combination. And I'll explain, as I said, very briefly how these tests work. There are a number of them, and they all help in different ways in fault finding on the machine, but they isolate the particular part of the machine you're trying to fault find on, and that's what really makes it so much more useful than trying to fault find with the full firmware installed. The machine firmware is not in the ROM at the moment. This is just test code. Okay, so this test we're going to look at is the one I actually showed in the previous video. It tests the RAM block 1. This is the bit of the RAM that's mapped into the lower page in the address space. It's very simple. It writes a value of AAAA to a particular RAM location, and then it reads it back to make sure it's correct. It goes through all the RAM spaces in this part of the RAM, except for one that we're using as a counter, and then it will do the same thing using the complementary value of 5555, and again reads it back. It will then loop back, do the whole thing again, and each time it goes through this entire process, I've got the analyzer set to trigger. The analyzer's set on the trigger for 10,000 events, so what it will actually do is count down the number of cycles that we're running on the test. So if I arm the analyzer and switch the HP on, you can see that up in the right hand corner we're counting down the number of full cycles. If any single bit failure occurs in this test process, then the count will stop. The software jumps to a hold loop at the end, and obviously that will stop the analyzer from triggering. As you can see, it's counting down quite happily, so we can be fairly certain at this point it's able to read and write to that particular block of RAM. So I'll stop there and I'll select the next test on the ROM by setting the next switch combination. Okay, I have the switch set for the next test. This is almost identical except that it tests the next block of RAM. This block of RAM is actually on the same card, the same memory card as the one we just tested. It's just the upper part of that memory card that has not been remapped. So the machine sees it as a separate block, but it's actually the same RAM card. And this part of the RAM memory space runs from 40,400, these are octal numbers, to 47777. But the test works in exactly the same way. So I'll start that running on the analyzer, and so you can see again we're counting down, successfully running the tests. This is obviously running slower because it's testing what amounts to a 4K block of RAM rather than just a few hundred bytes. But you can see it's getting through successfully each time. So it's reading and writing the two values to each memory address space. So I'll stop that, select the next test. Okay, the next test is identical except that again it uses a different memory address space. This is actually the memory address range of the second memory card, and that's not plugged in. I know it doesn't work, so it's not plugged in, so these tests should fail. In other words, we shouldn't see the analyzer counting. So I'll switch on the HP, and as you can see the count is stationary, it's not counting down, and that's to be expected. There is no memory card there, so it's just failing the test all the time. So on to the next test. I'll select the appropriate switches. Okay, so I have this test selected. This again is a RAM test of the first block of RAM. This is a much more complex test. There's several pages of code in this, and one of the things to bear in mind when testing this particular machine, or any machine that uses DRAM, which is dynamic RAM, is that you need to run tests in a specific way. And what you'll notice is in the first test I ran, I call it a board test, and this one is a RAM system test. And the reason I call this one a RAM system test is the way that a DRAM chip works is you can write data to it, and it will retain that data if you don't do anything else for just a few milliseconds. Then it will lose that data. And the reason for that is the data is just stored in a very small capacitor, and that self-discharges in a very short time. But in that period before it's lost its charge, you can read the data back, and it should be the same, of course, that you wrote to it. But the way that the DRAM is maintained so it doesn't lose what you've stored is at very regular intervals the DRAM is refreshed, and that's performed by a series of reads, and each read causes internal circuitry in the DRAM to refresh the contents that are stored. And in these particular RAMs, the time that's guaranteed to retain data between refreshes is 2 milliseconds. That is, if you don't refresh at least every 2 milliseconds, then there's a possibility the data could be lost. Now, in the previous test, what we were doing was writing a value to the DRAM and then immediately reading it back. So, in other words, we were reading it back within a few microseconds of writing it. So although the test proves that we can successfully address the card and that the RAM chips are working to a large degree, that is, they can be addressed, they can be written to, and they can be read from, what it doesn't prove is that the system, the memory system within the unit is working. That is, we don't know if the refresh is working. If the refresh isn't working, the first test we ran would still pass because we're reading the data back well within the required refresh interval. This test works differently. It will go through each block and it will write the test value to all the parts of the block that we want to test. It will then wait 100 milliseconds and then we'll go back through the same block and read all locations, looking for any errors. It does that with the 2 test values that we specified, and once it's done that for both values, it will be the end of a successful test run. So I just need to change the trigger address for this particular test. Okay, and we're ready to start the test. So I'll power up the HP, and again you can see it's counting down. And as I say, what it's doing here, it's writing all locations within this block. It's then reading all the locations after a delay, and the theory here is that between the writing and the reading, we're leaving 100 milliseconds, which should easily be enough to show up any issues if the refresh circuitry is not working. Okay, so on to the next test. As you might have guessed, this is identical except for the fact that it's testing the second memory block. So this is the remainder of the first RAM card. I'll just reset the analyzer so the count's on 10,000. Power up the HP. And as you can see, it's counting down. Again, it's much slower now because not only is it writing and reading the entire block, much bigger block, but it's also got the 100 millisecond delay twice in each loop. But as you can see, it is still counting down. If there are any errors, again, it would stop counting. I'll turn off the HP, select the next test, and this test is the exact same test but for the third block of RAM, which, as I said earlier, is the second RAM card. But as previously, that RAM card is not fitted. So as you can see, the HP is now on. The count is not going down. It started at 10,000, it will stay on 10,000 because the test will fail every time simply because there's no RAM card there. So these tests are very useful for testing the RAM cards. The RAM cards are very difficult to test from the electronic perspective. So using a scope or even a logic analyzer, they're quite tricky to test. But a test like this will confirm in less than 1 minute if the entire RAM card is working from the perspective of the machine. That is, can the machine successfully write to and read from all the locations within the RAM? And obviously it is doing that successfully here. Okay, on to the next test. I'll need to move the camera for this one. Okay, I've got the light turned down for this test. Now, on this machine, writing data to the display is a very complex task because the data has to be encoded in a certain way to write it to the display. So, for example, the 16-bit data value that's sent to the display contains information as to where on the display the data is to be displayed. And it's in 2 locations. It's a 32 character display, but it's effectively split into 2 16 character blocks. And when you select a location, you select a location in both blocks. In other words, if you select the first location, you select the location for the first character in the first block and the first character in the second block. And then you also include in that 16-bit word the value, the data value or the character value you want to display in the first block and the character value you want to display in the second block, which of course might be different. You then have to encode it in a certain way and send it through to the card. So again, this is a very good way of simplifying what is a very complex test on the electronic side. Not only that, but it's consistent. This is all it's really doing at the moment, so you don't get sidetracked with other things that might be unrelated. So if I now power up the HP, this test will start. So as you can see, what's happening, it's cycling through characters slowly on the left hand half, and it's cycling through the character set rapidly on the right hand part of the display. I don't know how well this is coming across on camera. It might be flickering because of the camera shutter speed, but there's no flicker apparent on the display itself. I've chosen a rate to give a sensible display. One of the complications in doing this sort of testing again is that the delays normally associated with writing to this display are generated by other activities in the normal function of the the HP. I'll start the test again. Because those processes aren't running, then I had to introduce other delay factors to make sure that the scanning rate for the display was sensible for the circuitry within the display system. But as you can see, it's working, and it gives me a very simple way to test the display. So this tests again the entire CPU, it tests the logic board for the display and the display board itself. I can halt this with another test. I've got a second test that runs this in the static mode, but I can see already that on the left hand side I've got a row missing across two of the LED displays, and also a weak column as well. I'll just restart the test to make it clearer. So you can see there's a row, but the row is on two separate LED modules, so I'm suspecting that might be a driver because they are driven as a common pair. So that might well be as simple as changing the driver for it. The missing column might be more complex to resolve, but again it could still be just the driver that's missing, that's here. But either way, it's much more straightforward doing it like this than it would be trying to put a scope on the various components and track down the faults that way. The right hand part of the display is just to allow rapid confirmation that the character generator ROM is actually working. So in short, this is a very simple way of doing very complex testing on the machine. It only took a few hours to write these firmware routines. It would be a lot quicker if I had a compiler, but I don't, so I've had to do it the hard way, writing machine code on the bit level and interpreting the various instructions. As you can hopefully see, this is now a very useful tool, and with the number of tests I've got in the ROM, this should hopefully really help me in resolving the issues with this machine and finally get it working. As ever, any comments or advice is welcome.